So now we'll draw the FBD KD for a motorcycle that's accelerating down a circular path. And what we're going to end up doing is drawing it halfway between points A and B. And the bike throttle, you're told, is accelerating the bike. So we're going to go ahead and draw really a great picture of a bike. Which looks like a block right there. That's real good. And so we're going to end up at a location. If we go halfway between A and B, then we would end up at 30 degrees from vertical. And we're going to end up using a normal tangential coordinate system because, again, we have movement on a circular path. So the normal tangential ends up working out very nicely. I've got the weight of the bike. I've got a normal force from the ground. And I also have the force of friction, which is what's accelerating the bike. We need to obviously put our coordinate system on here, T and N. Over on the kinematic side, I've got mass times the tangential acceleration, right, which again is the mass times the change of velocity. And working towards the middle of the circle, I would have mass times v squared over, in this case, it would be, 300 feet. So if we kind of look at our unknowns here, right, the force of friction is an unknown, something we're going to be able to calculate. We've got a normal force, we've got a velocity, and we've got tangential acceleration, or v dot. So we've got 4 unknowns here. And so we would say we are definitely going to need some kinematics. Right. Again, we only have 2 independent equations up there, so we're going to definitely need some more kinematics. All right, we got a child down at the park on a swing set being held in the position shown by a second child. We'll neglect the mass of the swing, and what we want to do is draw the FBD KD at point B just before and just after release. So we're going to start with the before release picture. And so we end up with a picture of the swing right there. We've got the weight of the boy. We've got a force that's holding it. And we also have a big tension force right there. So those are my 3 forces that I've got. I would end up putting that right down there. And over on the KD side, if it's before release, the acceleration is equal to 0, so I've got no forces on that side over there. So just after release, just after that, I'm going to go ahead and draw the, I guess I should be even better here, that's 35 degrees up there. It's obviously going to come into play here a little bit more. Now I've got movement on this circular path. So I'm going to end up using tangential and normal coordinates. And so I'm going to put those coordinates right here. And I've got over here, the only other force besides the tension is just the weight. And again, that's at 35 degrees. Over on the right-hand side, what have I got? I've got a mass times the tangential acceleration. I've got mass times v squared over r, the length of the swing. And just after release, just immediately after release, I would know that the velocity is still equal to 0. So this term goes away. And so now I've got acceleration in the tangential direction and the tension in the rope. And so just to finish this, we'll also do it right at the bottom. We go right at the bottom, right there, at the very extreme bottom of the motion. We'll go ahead and also draw the FBD KD. So I've got a tangential direction, I've got a normal direction, I've got the tension, I've got the weight of the child. Over here, I've got a mass V squared over the length of the swing, and in the tangential direction, I've got mass times AT. And I would see here, if I sum forces in the tangential direction, that would tell me that A tangential equals 0. So again, I'm stuck a little bit with being able to solve for the tension and the velocity. I've only got one equation left, so I would need some kinematics to get me through this.